All right, guys and girls, hopefully you can hear me. If you can't, then just scream on the chat because I'm reading the chat, obviously, and I'm not just flapping my mouth opening and closing. But welcome back to another live session with telescopes.net, and we have one heck of a jam-packed schedule for you, as we always do, and hopefully we don't run over too much time this particular event. So I have with me Bruce Waddington, who is one of the developers of PHD2. And just to give you a bit of history, for those of you who were around when Craig Stark originally developed PHD, these guys came along and picked up where he left off and just made the program what it is today. I think all of us can attribute our fantastic guiding numbers to a certain extent to these guys. But before we go ahead and let Bruce do his thing, we actually have a special promo for you guys who are watching this live stream at home, and you'll only get it by watching this live stream. Is if you look down below is the coupon code for 10% off almost every single QHY-CCD camera that we sell on our website, telescopes.net. That includes all the full-size cameras, the guide cameras specifically. We even have the Polemaster as a promo, and I believe their guide scope, I think it's like a mini guide scope or something like that. Just for you guys out there, so you know, this will be replayed because obviously I'm aware of the time zone difference. So once this is over with, this should go up live. You may have to give it a moment for it to encode so you can get the full high resolution version. All right, enough of me talking. Below me, I have Bruce. Hello, Bruce.
Hello.
So give us a little bit of information about yourself because not everybody knows who you are. So let's give these guys a quick, brief overview of Bruce.
Okay, we'll make it real brief. I've been monkeying around with telescopes and astronomy since like the mid-60s. And I went to school, I majored in astronomy. I did some research work up at Mount Wilson, spent some time in grad school in astronomy and astrophysics, and decided that really wasn't the way I wanted to make a living. So I spent the next 25 years in software development. And fortunately, when I retired, I was able to get back into astronomy. And so that's kind of what I'm doing here. It's the sort of thing that we do as amateurs. I picked up again around 2005, so the last 15 years or so, I've been doing the sort of astronomy that we're all talking about today. And I got involved with PHD2 right in the second half of 2013, and I've been working on that project ever since. So that's my story.
Excellent.
So
okay.
we're ready to go here?
Okay, it looks like we might have some issues with your side on the stream. Some of the audio was breaking up a little bit there, so hold on 1 second. I'll see if I can just bump up the bit rate on your side just in case. Would help if I actually had the right window open. Let's crank this up a little bit more. Okay, so if this happens again, what I'll probably do is just pause it and then just restart this stream. Oh look, Richard Wright is joining in for some weird reason. Hold on, let's pull Richard Wright in real quick. Always love it when we start off with technical hitches. Hello, Mr. Richard Wright. Hello.
Hey, sorry, I'm turning.
You're about an hour and 15 early.
What? Oh,
yeah,
3 hours to me.
Yes, Pacific time. My God, yeah. Look, this is how eager Richard Wright is wanting to get onto the stream. He's so pumped and ready to go.
I'm so ready. So my most of my day actually runs on mountain time. So I'm always adding 2 hours, and so that's what I did.
Oh wait, you're back home in Florida, right?
Yes. So.
Oh boy.
But I'm always like, okay, so 3 o'clock their time is 5 o'clock my time, and yeah. So okay, cool. That's fine. I will.
You know,
I'm
you
not
know
gonna
who Bruce
crash.
is, right?
Yes, I know who he is. We've probably met and shook hands sometime, I'm sure, at a conference or something. Hi,
AI,
Bruce.
Yep. Hi,
probably
Richard.
AIC.
Hey. Yeah. AIC or knee for things like that. We all bump shoulders. So
Awesome.
I'm sure in other lives, Bruce is is a software guy like me. So
Oh yeah.
I'm sure we have a lot in common outside of astronomy as well. So, but
All right, I'm going to kick
okay.
you off now.
Yes, I
'Cause
am bye. I'll be back in an hour. All right.
Okay.
All right, bye.
Oh, that is amusing. There we go. All right, Bruce. Sorry about that. I wasn't
That's all right.
expecting Richard to suddenly appear out of thin air. Okay, so the floor is all yours. Take it away.
Okay. What I'm going to do is walk you guys through a presentation on PHD2, and I'm not going to spend a whole lot of time on some of these slides. I think most of the emphasis here today is on more of the technical details and answering your questions. But it's probably useful to go through some of this. And in the process, I'd like to address some common misconceptions that people have or point out areas where people regularly get fouled up. And that might help answer some of the questions even ahead of time. So this is the basic screen layout. If you've used PHD2, you know what this looks like. If you don't recognize it, then you're probably paying attention to the wrong conference here. And we'll come back to this stuff. Just as a point of terminology, we have this thing, this rectangle, which is the search region. And that's the area on the camera sensor in which PHD2 is actively looking for the guide star as it moves around. It can be enlarged or shrunk depending on what options you choose. The lock position is not something most users think about, but that is the point where the guide star started, and that is the target for the thing. So the effort of PHD2 is always to push that guide star back to the lock position. And then, obviously the guide star itself may be some little distance away from that. This comes into play, this terminology matters a little bit when we talk about dithering, because most people, or a lot of people, get confused about how dithering works. They don't know how much to dither, and we'll come back to that in a little while. Another thing that is just a reality is that there's really two systems of axes here. There's the camera sensor axes, which are the X and Y coordinates of the individual pixels that are on the sensor. And that's always going to be aligned left, right, up, down on the screen when you're looking at the display. The orientation of the right ascension and declination axes in general are going to be different. They're shown here with the red and blue lines. And one of the notions that people have occasionally is that it's really important for them to try to align the camera so that these axes line up. So they worry about rotating the camera to make them line up, which is entirely unnecessary and actually doesn't buy you anything at all. So if you hear advice that says that it's a good idea to do that alignment because it makes the guiding easier or more accurate, that's not the case. This is all just basic math, basic trigonometry here. And PHD2 does it regardless of how you happen to have the camera oriented. So this is just a look at what happens when you don't guide. This is kind of the basic, kind of baseline for why you do guiding at all. In this graph, the declination is shown in red, and then the right ascension is in blue. And the idea is that with virtually any telescope setup, there's going to be some drift in deck, and that's going to be caused by misalignment on the pole. And the polar alignment error is never going to be perfect. And so you're going to get this declination drift. And then the blue line is representative of what most mounts produce in right ascension. And there's two things going on here. The most important being this slow oscillation that you see, which is caused by uncorrected periodic error in the RA drive. And that, again, for most gear-driven mounts, is just a physical reality. It's not possible to machine those things absolutely perfectly. And so there's typically some uncorrected oscillating kind of movement like this that we refer to as periodic error. So these are two things that you hope to control when you do guiding the way we talk about it here. And then, of course, overlaid on both of those things are all these relatively high frequency humps and bumps in the curves. And that's going to be mostly due to seeing effects, although in some cases it could be caused by other things, gear roughness or vibration in the system, things of that nature. But this just answers the basic question of why does anybody bother with guiding at all? And of course, with some mounts, you don't need to do this if you have other ways of controlling the drift, and there's essentially zero tracking error in right ascension. But those are typically very expensive mounts. So now what we look at here is just the real high level picture of what is involved in doing guiding. And the idea is, well, obviously you capture an image, you take a picture of the sky with your guide camera, and it's then up to the guiding software to locate the guide star and compute exactly where it is on the sensor. And then it's going to look at that and say, well, that position isn't exactly where I want it to be, so I need to compute how far should I move that guide star to get it back on the lock point. And so that involves this mapping I was talking about earlier, where you're mapping from the camera axes to the mount axes, and you determine what are the right commands to send to the mount to move it a little bit in right ascension and a little bit in declination. And we send those guide pulses down to the mount. We hope the mount does what we asked it to do, and then we cycle around and take another image. So you basically do this all night long, just rinse and repeat, take a picture, measure the guide star, send some guide pulses, take another picture. So if we look at this now from a PHD2 perspective, everything that's on the right-hand side of this thing is basically controlled by PHD2. So the capture of the image is going to depend on what exposure duration you've set, whether or not you're using dark frames or bad pixel maps to clean it up. The goal is to have a nice, clean, relatively noise-free image to work with so that you can identify a guide star with a lot of accuracy. And then we compute this guide star centroid, and that is typically down to about 1/10 of a pixel, assuming that you have a decent focus and a decent signal to noise ratio on that star. And then, as I said before, that gets taken and translated into how far the guide star has moved from its lock point on both the RA and DEC axes. And that involves, the use of the guide algorithms that you guys are aware of, how good the calibration was, all those kinds of things. And then we send the guide pulses down. So as I said, everything on the right are things that as developers we've worked on very hard in PHD2 to try to refine these activities, make them as accurate as possible, make them as automatic as possible. And then at the end of the day, we send these guide pulses down to the mount. And from that point on, there's not much we can do to improve things. And in fact, it comes down to how well the mount behaves and what the seeing conditions are. Now, the goal for this kind of guiding is to have guiding results that are limited by the seeing. There's nothing we can do about that. I can talk a little bit more about that in brief in a little bit. And the impediment there is whether or not the mount is performing well and to what extent it's doing what it's told with these guide pulses. So it turns out that probably 95+% of what we work with on the support forum is on the left-hand side of this, which is the mounts aren't working well or the seeing conditions aren't adequate. We spend not really much time with this whole right-hand half of the chart worrying about guide algorithms and parameters and things like that. So one of the things that is very different about PHD2, certainly different than the original PhD, and that is that the default settings for all these guide parameters are configured on the fly for the particular configuration that you've defined. Now, to do that, we want you to use this profile wizard to define what those configuration settings need to be. So we need to know what kind of a camera it is, what the pixel size is, whether or not you're binning, what the focal length of the guide scope is. These are all things that you're walked through in this wizard interface with the new profile wizard. And based on all of that input, we compute what would be a sensible set of guide settings for that particular configuration. And our expectation is if you do all those things and you input the numbers correctly and the mount is behaving, you should get very reasonable results out of the box. You should have to spend almost no time fiddling around with guiding parameters. And this is counterintuitive to a lot of people, but it's the way that the program is designed, and it's what our experience has shown works the best. One of the questions that you see on a lot of forums, you'll see somebody say, well, you know, I've got this John Deere Model 500 mount. Somebody needs to tell me what the right guiding parameters are. And of course, that question kind of misses the point. It all boils down to the details of the configuration, and in particular, what the image scale is for that guiding system. And that's going to have not much at all to do with what kind of a mount it is. So we'll come back to this later. I really urge people to use the new profile wizard to configure these settings. You can go in, as you know, and you can try to do this stuff by hand. You can change your camera, change the mount setting, but what you end up with is you get into a big goat rodeo because you establish some of those settings correctly, and then others you forget about, or others that you don't know about, things like min moves and things of that nature that are normally set for you behind the scenes don't get set. And now you've got an uphill battle trying to resurrect all that and reconstruct what would have been done for you if you'd used the new profile wizard. So that's one of the messages I hope we can hammer on here. One of the things that we do, as you've noticed on the support forum, is we encourage people to use either ASCOM or Indie mounts, depending on what platform you're on. We use those mount connections for guiding. The reason is that when we have those connections, we have pointing information available to us in PHD2. And that means we can do a lot of the work for you in terms of automatically adjusting when you do a meridian flip, automatically adjusting the guiding rates based on where you're pointing in the sky, whether it's near the celestial equator or it's further toward the poles. And it also, by the way, avoids all the problems that come with these ST4 guide cables. For whatever reasons, these cables tend to be kind of fragile. People often are putting them on, taking them off for each time they set up. And the conductors in these cables get broken or they get damaged and they short. And so it's not at all uncommon for somebody to find out that the mount isn't guiding at all in one direction or another, and it's because of damage to these cables. And of course, if you eliminate the ST4 interface, you eliminate the cable. It's one less cable you have to worry about. And then finally, from a support point of view, it allows us to do better diagnostics and more of these sanity checking capabilities that we have in PHD2. The more we know about your setup, the more we can help you get the best guiding results. And a lot of people don't like these sanity checking things. You know, you'll get an alert message at the top and it seems like kind of an intrusion. But the philosophy is it's better to know than not know. And it's better to know early in the session so you can do something about it instead of wasting an entire night and then find out after the fact that something wasn't working that you could have known about. So this is a picture, as it turns out, of one of Andy's old setups. He's trying to illustrate where to do a calibration because we have a lot of people who don't seem to know where the celestial equator is and have trouble knowing where this ought to be done. What we encourage people to do is to do the calibration somewhere within 20 degrees of the celestial equator if they can. They don't have to. And it's only because in those locations we're going to get the highest quality calibration measurements because the greatest apparent motion of the guide star in RA happens near DEC equals 0. So the advice here, particularly if your mount has backlash, is to manually nudge the mount north with the hand controller until you see the stars on the display start to move. That basically manually clears the declination backlash. And then when you do the calibration, that backlash, which is still there, is not going to have any effect on the calibration results. Now you say, well, what is it the calibration is really doing? There's really two things. One is we're trying to understand what the orientation of RA and DEC is relative to the XY coordinates of the camera sensor. So that basically is what the angle is of your guide camera. And the second thing is just what the rate of movement is in RA and DEC when PHD sends guide commands. So this just gets boiled down to measurements of how many pixels does the guide star move when I issue a guide command of X number of milliseconds. And that's all there is to it. And as it turns out, we only measure those rates for the west motion in RA and the north motion in DEC. And that's why you can get away with manually clearing the backlash by doing some north moves right before you start. Even if the scope and the mount don't respond going back south and the guide star doesn't ever really get back to its starting location here, it doesn't matter because the calibration results don't worry about them. If you get calibration alerts, which you may do, it's a good idea to pay attention to them. It's probably telling you something that's likely to be a headache downstream once you start actually guiding. You can always look at the calibration results. This is an example of the review calibration results dialog. You can see what the angle of the camera is. You can compare the expected and measured rates. You can know how many steps were taken, what the orthogonality error is, all those kinds of things. Most people don't look at this, but if you have an alert about a calibration or you have some concerns about whether it was done accurately, you can always bring this up and look at it right away. You can also look at it after the fact. This will always show the results from whatever the most recent calibration was. So then this takes us back to something I mentioned earlier, which is that we would like for guiding to be seeing limited. And so you'd say, well, why can't it be better than that? And the reason is that you really can't conquer seeing with this kind of guiding. And by seeing, what I mean is turbulence. It's not transparency or light pollution or any of those things. It's the jitter that you see if you happen to be using it visually with an eyepiece. And this stuff is caused by atmospheric cells in the Earth's atmosphere, and they're cells that have different temperatures. So you can imagine that this is equivalent to having a few zillion tiny little lenses up there in the sky, all of which are lining themselves up and moving around and changing as that column of light comes down to your scope from whatever star you're looking at. Now these fluctuations happen at very high rates, hundreds to thousands of times per second. And there's simply no way that you can correct for those kinds of high frequency effects. And in fact, when you try to do that, what you end up with is what's called aliasing. And so you can actually make it worse by trying to use super high frequency exposures and guide at very high rates. It simply doesn't work. It's also worth remembering that the seeing conditions can change a lot from one night to the next, and even from 1 hour to the next. I've had situations in the last couple of weeks where I've seen the seeing go from around 2 arc seconds to over 3 in the space of about 10 minutes. And then 20 minutes later, it was right back to 2 arc seconds. So seeing is something you always have to be aware of, even though you can't do anything about it. It's something you want to be aware of, and not beat your head against the wall trying to get really top-notch guiding and imaging results when the seeing is poor. Here's a picture of the kind of effect I'm talking about. I don't know if you can see this very well. The top graph shows the raw guide star positions when we're taking images with half-second exposures. And you can see this guide star is just bouncing all over the place. And it's kind of living in an envelope of maybe plus and minus 1 arc second in this example, which is not good at all. I mean, you're hoping to be able to guide much better than that. If we drop that down to longer exposures, what you see is that envelope gets much smaller. So we're basically averaging out a lot of this jitter in the star position. And now we're seeing apparent movement of the guide star that's more like plus and minus 0.2 arc seconds. So that's one of the reasons why we encourage people to not try to use super high exposures rates, super low exposure times, and to go with longer exposures, 1 or 2 or 3 seconds, to help average out the seeing effects. So the fact of the matter is that, the longer exposures basically let the sensor do some of the work for you. You're averaging out the position of that guide star. It also allows you to capture dimmer stars, which is particularly important if you're using an OAG and a long focal length setup where guide stars are not plentiful and the ones that are available may be relatively faint. You have to balance this though, because depending on the mount, you may need to have shorter exposures because the mount doesn't track well enough natively. And so if you take long exposure times, there's too much time there for the mount to basically wander around off track and increase your guiding error and degrade your imaging results. So as a general rule, we don't recommend exposures below 1 second, and how much above 1 second depends a lot on the quality of the mount and the quality of the seeing conditions. The guiding assistant, which we'll talk about in a little while, helps make recommendations for what that should be for your setup. This is an example of what we would consider to be well-behaved guiding. And the point here is that the guiding in deck should be relatively infrequent. And the reason for that is that the deck motor isn't running at all normally if you have an equatorial mount. And so the only thing you really want to be guiding for in declination is slow drift. And so if assuming you're reasonably well aligned on the pole, that shouldn't require very frequent guide commands. Now in this example, you see these big pulses here. That's because I was using deck backlash compensation. There's a little bit of backlash in my mount. But you can see that the deck activity level is maybe 10%. 90% of the time, the guide star is close enough to the mark that we don't have to issue a guide command at all. Our right ascension is a different matter because there the mount is running. There's going to be lots of direction reversals in RA. There's periodic error to deal with. So you would expect that the guide commands will be issued much more frequently. But of course, in RA, we don't have to worry about backlash because there isn't any backlash in the RA drive as long as you're guiding at a rate of less than or equal to 1x sidereal. So this is how we would like to adjust the guiding parameters, in particular the min moves, so that you get these relatively low correction rates in declination. So just to kind of march you through this, if you're doing a first-time setup, you want to make sure you get the latest versions of the software, the latest versions of the camera drivers. If you're going to use mounts like that use EQ mod or the SkyX, there are recommended settings for those things because of the way they behave. Those are posted on our website, and we routinely pass those on to people who ask about them. We recommend that people use guide speeds of at least half X sidereal. The defaults, for example, for EQ mod are much, much lower than that. They're like a 10th X, and that really results in subpar guiding results. And you also want to be sure you disable any backlash compensation that you have set in the mount firmware. And again, use the new profile wizard to build this profile. Be careful about the parameters you enter. And if you work through that process and provide all the right answers, you're going to have a baseline group of settings that are likely to perform very well. So, first night under the stars, get a rough polar alignment, do your first calibration along the lines that we just discussed. Let PHD2 auto select a guide star, and then run the guiding assistant for a few minutes and get your first view of how that mount is going to behave. Now, as part of this, and as part of the PHD2 package, there are a lot of these specialized wizards that are there, and mostly these are there for either to help you understand what the mount is doing or to help you with tasks that you don't do all the time. For example, when I relocated my scope, I had to do polar alignment. I hadn't done a polar alignment in 8 or 9 years, and I only roughly remembered how to do it. But so I just used the polar alignment wizard in PHD2 and got it done very quickly. So you might want to take a look at these tools and make sure that you're familiar with them, you're at least aware that they're present. The guiding assistant is probably the most important of these, and what it's trying to do is look at how the mount behaves when guiding is disabled. So that allows you to see how the RA gear is tracking, what kind of residual periodic error you have. It will allow you to measure the backlash that you have in declination, gives you an estimate of your polar alignment error. And finally, it looks at the frame-to-frame displacements in deck, again, remembering that the deck motor isn't running. And that's used as a way to estimate how the seeing is. And that gets translated into recommendations, again, for some of the guiding parameters. So when you run the guiding assistant, you typically let it run for 2 or 3 or 4 minutes. You get a bunch of statistics here that we won't go over in any detail. There's no time. And then on the right-hand side, you get a set of recommendations. And it's good to pay attention to these. And the ones where you can automatically apply them, that's really what you should do. Just click on the apply button, and it will apply those settings. In this case, for example, there was a deck backlash measurement that came out to be just under 400 milliseconds, which is pretty small. And so the recommendation here is to go ahead and enable backlash compensation. And if you click on that apply button, that all gets done for you automatically. You don't have to worry about it anymore. So this is certainly something you want to do anytime you have a new setup, or you have made changes into the mount mechanics. And it's also good as a way to check the seeing conditions on any given night. There's usually no point in rerunning the backlash test over and over again. Unless you've made mechanical changes to the mount, not much is going to change. So there's no point in spending any time doing that after you know what the backlash situation is for your mount.
Just a quick question, Bruce.
Yes.
Just to cut in there. Go back to that slide for 1 second.
Yeah.
is this applicable if I was to if I was to break down my mount every night, or is this more for permanent setups? Because I know someone's going to ask you that in a second.
No, it really doesn't make a lot. I mean, from the standpoint of the backlash, it doesn't make any difference that you tear the mount down and you put it back up, because the backlash is a property of the drive system, so that's going to be the same. It's useful to do this if you've just set the telescope up. You can just run it for a few minutes. It will probably sanity check your polar alignment, because you probably had to do the polar alignment again every time you set it up. And again, it also gives you a measure of what the seeing conditions are like for that night. But it's not critical that you do this every time. It's up to you. This is an example of a backlash measurement that was done. And you can see what's going on here is that the guiding assistant takes control of the scope, and it sends a whole bunch of north pulses. That's what these green things are on the left. And then it stops sending them, and it turns right around without doing anything else, and it starts sending south pulses in the opposite direction. So if the mount was perfect, you would get this white line. You would immediately reverse direction, and you'd go back to exactly the point where you started. Obviously, we don't live in a perfect world, and this flat spot is what we would refer to typically as backlash. I mean, technically, it's reversal delay, because we don't necessarily know what the mechanics are behind this. But the idea is that once we started issuing south pulses, nothing happened, right? The guide star is just sitting in the same position. And it took 1, 2, 3, 4, 5 guide commands of 500 milliseconds each before the mount finally started to move. And then once it got moving, it moved along just fine. So that tells us that this mount, in this case, had something north of 2.5 seconds of backlash. This isn't a horrible result. It's a little high. It's something that could probably be handled pretty well by the PHD2 backlash compensation. Here's an example of a nastier situation. And again, you see we have the flat spot here that's probably backlash. But then even once the axis gets going, it kind of wanders around out here, and then it flattens out again. So this is probably stiction. There's some kind of static resistance in the axis out here. It could be caused by real serious imbalance or some kind of static resistance. But this is going to be a hard problem to guide out. And it's not something that backlash compensation is likely to deal with very well. That we would tell people here that they really need to go and look for some kind of mechanical improvement on the mount to make this go away. And again, and this comes back to your question, Simon, what do you do with portable setups? One thing you can do to shortcut things is to keep track of how the guide camera is oriented relative to the guide scope. You can do that with just some painter's tape and pencil marks on it, so you get it back at the same angle. Make sure you have a tight focus, do a quick polar alignment, and get going. And you might run the guiding assistant here if you wanted to check the seeing or check your polar alignment, but you might not. And with a permanent setup, you basically, restore the calibration and just go. One thing to keep in mind is that a lot of this initial setup can be done well before it's truly dark. You just need to have the sky be dark enough that you can find a guide star. So you can get all this housekeeping out of the way before you're really ready to start imaging. Polar alignment is another thing where people tend to get fixated a little bit on super high accuracy for polar alignment. We generally don't recommend that. As it turns out, because polar alignment error just produces a nice steady drift in deck, it's actually easier to do guiding when there's more polar alignment, because you don't get all the direction reversals in deck, and therefore you don't run afoul of whatever backlash is present in the mount. You don't want to go too far with that, because at some point you're going to get field rotation. As a general rule, I would say anything below about a 10 arc minute error, which sounds like a big number, is going to get you perfectly reasonable guiding results, and you won't have field rotation. So the point here is that there's no point in obsessing over the polar alignment accuracy. It's not likely to have much of an effect on your guiding or your imaging results. So let's talk about, I mentioned earlier, the mount is usually a limiting factor, and just going in, there are certain kinds of things that you can expect to be an issue with most mounts. We've talked about this a little bit. The reversal delays in deck are going to be there for almost any geared system, assuming it doesn't have absolute encoders and assuming it isn't belt driven and all those other things. So that's going to be something that you have to think about. And fortunately, if you have only a fairly modest amount of reversal delay in deck, you can use PHD2's deck backlash compensation. And this is not like the backlash compensation that's programmed into most of the mounts. And the reason is that this algorithm is adaptive. So it's self-monitoring and self-adjusting. It continuously changes the size of that compensation based on how things are going. It's important that whatever backlash compensation is in the mount be disabled. If that's enabled in the mount, you'll typically get oscillations in deck that won't ever stabilize, and you basically can lose an entire night's worth of imaging that way. The reality of this is that the amount of backlash in deck is typically dependent on the pointing position, and that's what the mount implementations don't take into account. And that's why you have to have this adaptive mechanism in order to figure this out and make adjustments. If the backlash is really severe, we recommend that people do what we call unidirectional deck guiding. That just means you're only going to guide north or south, but not both at the same time. And again, if you have polar alignment error, that actually works very well. And I've seen people get really good imaging and guiding results operating this way. This is an example that relates back to some of what I mentioned earlier when I showed you that really nasty backlash measurement graph where there was a combination of backlash, delay, and then stiction. And what you see, this is a typical example that you'd see where you try to reverse direction in deck, nothing happens for a long time. And then finally it gets going, but then it overshoots. And this is the stiction part of the problem, okay? So this is something that is absolutely going to require a mechanical improvement on the mount itself in order to make this sort of problem go away. Or you have to guide in just one direction at a time. Looking at the other axis in right ascension, almost all mounts are going to have some amount of uncorrected periodic error. This is just a reality of the mechanical process that makes that drive system. And we often get the question of whether or not it's okay to use periodic error correction with PHD2 guiding. And the answer is yes, that's what you want to do, assuming that the PEC in the mount is well implemented. We have seen cases where some of the mounts do kind of a harebrained implementation of periodic error correction, and in that case, it doesn't typically work very well. But for most mounts where the mount programming is done well and the periodic error correction is done actually in the mount firmware, that's going to definitely help guiding. What it means is that PHD2 basically doesn't see all those problems that are being corrected in the mount. So the guiding deflection is handled before PHD2 ever sees it. And it just basically means that PHD is looking at what appears to be a better performing mount. And then PHD2 is just handling whatever residual errors weren't corrected by the periodic error correction in the mount. There is an algorithm that's come along here in PHD2 in the last couple of years. This really was a rocket science project. It was done as part of a PHD2 thesis by a postdoc over in Germany. And what it is, we call it predictive periodic error correction. The idea is that it's a machine learning implementation that looks at the performance of the RA tracking as the mount is running, and it builds up a correction model on the fly and applies those corrections in a predictive fashion. This again works very well when there's PEC programmed into the mount. So it's complementary to the mount PEC, and it handles the kinds of things that typical periodic error correction can't. Most of you are probably aware that periodic error correction in the mount can only deal with what are called harmonic frequencies. So these are integer fractions of the worm period. But depending on the gear system in the mount, you might have recurring errors that aren't at harmonic frequencies, and those can't be corrected in the mount firmware, but they can be handled by this PPEC, predictive periodic error correction algorithm. And I've seen cases where people were getting 15 or 20% improvement on their RA tracking by using this algorithm. So it's definitely something to try if you haven't done so already. You know, coming back to all the other kinds of problems that people have, and you know, I don't want to go into this in great detail, but everybody has these problems. It's just a question of whether you recognize them for what they are. You know, typically you'll be chugging along and the guiding's going okay, and all of a sudden the guide star seems to lurch off into some direction or the other by a large amount. And the inevitable question is, well, you know, is that because PHD2 did it? And the answer is usually no, almost invariably no. And it's because of something else, some external event that happened that caused that excursion of the guide star. In a lot of cases, it's because something on the guiding assembly itself moved. You know, something slightly loose, something, people are using rings on the guiding scope, and you know, over a period of time, and as the scope moves around, these things can loosen up, and you get these little tiny movements in the guide scope and the guide camera. And a lot of people don't understand just how sensitive that all is. So let's take an example where you're using a guide camera that has 3 micron pixels, not unusual these days. So a 1 pixel movement of the guide star can be created by simply touching that guide camera and moving it by 3 microns. Well, 3 microns is less than 1/10 of the thickness of a human hair. So there is that level of mechanical precision involved here, because these little tiny displacements of the camera can maybe produce errors that are many arc seconds in size, and your guiding and your frame is lost at that point. Just finishing up on other problems that you hopefully don't experience, but certainly when you get new gear, or particularly when you change computing platforms, you'll oftentimes run into these timeout problems. Again, these are not caused by PHD2. These are camera timeouts, and they're usually related to things in the lower parts of the system, notably USB related problems. Sometimes it's bandwidth, sometimes it's power delivery. There's a whole list of things here that you have to go and unfortunately diagnose. The only good news is you can do this during the daytime. You don't have to waste dark sky time doing it. And unfortunately, it can also be due to out of date or buggy camera drivers that don't handle these things very well. Just to kind of wrap up here before we take questions, I think there's a sense in some parts of the community that PHD2 is really only for the lower cost, lower end mounts, and that isn't the case. You know, we have users who are using this software on very high end, very high quality mounts. And what you do in that case is you really dial back how much you're trying to do with guiding, because you don't really have much you have to do. So you definitely can use the guiding assistant recommendations for the min move settings. Remember, that's seeing related. And then you use algorithms like low pass 2 or hysteresis for both RA and DEC, because those are going to emphasize the slow kinds of corrections that need to be made. And you're not going to be wrestling with things like high periodic error and high frequency errors that need to be dealt with. You can also afford to use longer exposure times, again, because the mount is generally taking better care of itself. Just quickly, if you don't know, there are now a number of imaging and automation applications that know how to use PHD2 natively. A lot of those are relatively low cost. Some of them are even free. And this is all because there's a very extensive server interface that's built into PHD2. So you communicate with the application over a network connection, and you can control just about anything you want to that way. There also are what we call integration or coordination packages for these automation and imaging apps that don't know how to use PHD2. That includes MaximDL, CCD Commander, CCD Autopilot, applications like that. You're going to need to do this if you are expecting that you're going to just fire things up and go to bed and let it image all night long, and then you're going to get up in the morning and harvest wonderful images. We have a lot of people that think that's how things ought to be. And you're going to need to have fairly sophisticated automation and control apps if you're going to have success doing that. I think maybe we should tie it off here, Simon, because it looks like we only got about another 15 minutes. I think you said that there are going to be a lot of questions. So maybe we should just hold the presentation here.
There really is a handful, but I am going to say this. Some of them are hardware related. I'm going to make a quick point to you guys who are sending out these questions. If you're asking about backlash on your mount, PEC, things like that, this is probably questions you would ask the manufacturer versus this particular situation, because as mentioned in the actual program of what Bruce was talking about, a lot of this stuff can be identified to be with the mount, not necessarily the program, because a lot of people like to point the fingers at the software, not the mount, because at the end of the day they spend $2, $3, $4, $5, $10,000 on a mount thinking it's infallible. So always start with the manufacturer first to ensure and to rule out any of those problems. But let's go into some of these questions, and I'm sure people are already twitching here because you just started to talk about dithering, and I'm sure everybody, you know what, go through the dithering thing, because I know everyone's going to ask about that, because I'm going to get the walking noise question in a minute.
Okay, all right, let's talk about dithering. People have a little trouble figuring out, who's driving the car here when it comes to dithering. And the answer is that it's really up to the imaging application to know when to dither and how much to dither. PHD2 is just kind of doing the donkey work and making it easier for the imaging app to know when it's time to resume the next exposure. So the idea is that through the server interface, the imaging app can say, I want you to dither by X number of pixels, and I want you to let me know when the guide star has been restored to that position. Remember, now we're moving it to the lock point. And I want to know when the guiding has stabilized. And the imaging app can say, this is what I mean by having it be stabilized. In other words, I want it to be guiding at less than 1 arc second for a period of 10 seconds, whatever you want. PHD2 also controls the manner of the dither. So the default setting is that it's random, meaning that it picks a random amount up to the limit that's told it by the imaging app, and that'll be applied in both RA and DEC. For some mounts, that's not a good choice. particularly if there's a lot of backlash. And so we have this spiral mode dither, where basically we march that guide star around the original lock point in a clockwise direction, and we keep each time we make a circuit, we increase the amount of the dither. So this works well if you have a lot of backlash. It also works well if you have to dither by large amounts. And so this comes back, I think, to what Simon was alluding to. You have to decide how large the dither should be. And in order to do this, you need to think about the image scales that are involved for both the guide camera and for your main imaging system. So what you basically have to do, and this little equation here just gives you an example, you have to figure out if I dither by X number of pixels on the guide camera, what is the equivalent move in pixels on your imaging system? And if you have something like a DSLR and you have a lot of fixed pattern noise, the advice typically is that you need to dither by relatively large amounts, and you don't want those frames to end up being, tracked right back on top of themselves, which is why the spiral dither is a good choice for that. With spiral dither, the frames will never be exactly aligned. You won't have that problem, and you can use relatively large dither amounts and clear up a lot of that fixed pattern noise. So hopefully that gives you the basic idea. But it's important to remember what the roles are here. When you set this stuff up, you're really going to do it through the imaging app, other than choosing what dither mode you want. Does that do it, Simon?
Oh yeah. Okay, so let's start getting into these hardcore questions then. Like I said, I'm just gonna skip over the hardware related ones because, like I said, it's not necessary PHD2. So let's start with this one. Is full frame guiding still being worked on, and is it a big improvement?
It isn't being actively worked on. We're still, thinking about it. It's a lot of work. And actually, in a lot of cases, it's not likely to produce a lot of benefit. The only place where it's likely to make sense is if you have really badly malformed guide stars, or you have incredibly faint guide stars where it's difficult to get adequate signal to noise on a guide star. Other than that, it's not likely to result in much of an improvement. And there's some basic math behind that statement. At the end of the day, it all comes down to the signal to noise ratio that you have in that frame. And so if the signal to noise ratio is really low, you're not likely to get very good guiding results. That's just the ugly truth of the matter. But we know that there are applications where it would be a nice thing to have. And we have done some preliminary work on it, but frankly, neither one of us has been able to get enough time in the last 6 months or a year to really go after this.
And plus, I don't really see how this will be useful, especially if you're using an off-axis guider with a very small pick-off prism. So it's...
Yes, but you have to recognize there that you still have to have some signal in that frame.
Right.
Okay. You can't just guide on nothing.
Well, that's what we wished we could do.
Yeah.
Okay. What exactly are the pulses, and how important is accurate focus?
Okay. Well, the guide, what I refer to as pulses, are guide commands that are sent to the mount, and it basically says, I want you to turn this axis, whichever axis it is, RA or DEC. I want you to turn that axis for X number of milliseconds in either the north, south, east, or west direction. That's a pulse. And PHD2 issues that command, and it waits for the mount driver to report back that the operation has completed. As far as focus is concerned, I guess this is also another area where there's some old advice that's no longer relevant. We want people to get as good a focus as they can on the guide camera assembly. And again, this comes back to what I just was talking about. The accuracy of computing the guide star position is proportional to the signal to noise ratio. So the better the signal to noise within reason, the better the guide star calculation is going to be. That centroid position depends on SNR. Well, you're going to get the best signal to noise ratio if those stars are well focused. If you end up with out of focus star images and they're just these big mushy kind of fuzzy stars, then the accuracy of that calculation is going to degrade. So get as good a focus as you can.
Okay, you actually answered the other question that I was about to ask, but I'll ask it anyway. Is PHD using a centroid calculation or a peak irradiance sensing for determining the guide star positioning?
It's a centroid calculation. Yeah, it's a centroid calculation.
Yeah. Okay, so this guy is asking about a Celestron mount specifically, but I'm going to say any low-cost mounts. Do any of the low-cost mounts, is what I'm paraphrasing it as, are they up to the task for using PHD2?
Yes, they are. I mean, most of us didn't start out with, $10,000 mounts. So it really is a question of having reasonable expectations about what the mount is capable of doing. So, for example, on the lower end mounts, you're probably going to have a whole bunch of declination backlash that you might not be able to do anything about. That's okay. You can guide in only one deck direction, north or south, and not run into that problem. You're also going to probably have a considerable amount of periodic error in RA. That's also okay if it's reasonably smooth. PHD2, and particularly with the predictive PEC algorithm, actually does a pretty good job of dealing with that kind of periodic error. So it really comes back to balancing, where you are in the hobby, what your expectations are for the quality of your images, and understanding what your mount can do. Just to give you one example, personally, when I started out with all this, I was using a Meade LX200 mount. It was a fork mount. It was on the hideous Meade wedge of the day. And I was very happy. I mean, I was learning how to do this stuff, and I was taking pictures of deep sky objects, and I was amazed. I just loved it. And over time, I refined the behavior of the mount a little bit, and I could get down to, 1 arc second or 1.5 arc second guiding performance. And I thought it was great. And then it was only when I began to be more ambitious about what kinds of work I wanted to do, the quality of the images I wanted, that I decided it was time to upgrade the mount. But there's nothing at all wrong with starting out with a lower end product, as long as you don't expect magic to happen.
Right. I think that's a key factor that right there is the budget that you put into all of this is also a good determining factor, but it's not always the main case. Normally, I would say for people that buy lower cost mounts is don't go crazy with your focal lengths. Keep it to like around about 600, maybe 700. Anything more than that, I kind of find it's a bit of a struggle.
Yes, I agree with that. If you want to get into the hobby and learn imaging, the best way to do it is with a reasonably, short to mid-range refractor for your primary imaging setup. And then the flaws of the mount are not going to be that big a problem for you.
Right. Okay, so this is actually one that I've seen dozens of times, and a lot of people have chimed in on the live chat, but I might as well ask it anyway because we want to hear from, the master at the end of the day. Why do my graph numbers look great, but I have elongated stars?
Well, the most common reason for that is that you've got differential flexion. So a typical recipe for this to happen is that you're imaging with, a fairly long focal length setup. Maybe it's up around 2000 millimeters. Unfortunately, this is, right in the range where some of the Meade and Celestron SCTs put you. So you're trying to image it at a focal length of 2000 millimeters, let's say, and you're using a separate guide scope. Maybe it's a full-on guide scope, maybe it's one of these little finder gizmos. And the problem there is that you're going to have mechanical flexure, differential mechanical flexure between the guide scope and the main scope. And so PHD2 is maybe doing a fine job with the guide scope, and it's keeping that star right on the mark. But meanwhile, that other big telescope is moving around on its own, and that creates elongated star images. So that's the most common problem. The other problem is when you say, well, gee, the guiding results look really good, you have to be looking at that quantitatively. So you want the RMS numbers for DEC and RA to be reasonably balanced. If you're starting to get into a situation where, for example, the RA is twice as big as DEC, that can also be a reason that you'll get elongated stars in your main images.
That's going to open up a whole can of worms. I'm going to tell you that one. Okay, let's. There was one I was just looking at that is a good one. Oh, I know what they're referring to. I seem to have problems with centroid moving. I seem to have problems with centroid moving around a lot on the track star. Is this something to be expected or an issue I could solve?
It's not something you probably need to worry about. First of all, when you're looking at the star profile tool, you have to remember that's kind of an integer representation of what's going on. There's a bunch of rounding that has to go on there because it can only put that highlighted spot at 1 pixel or another. It can't put it, at a half pixel position. And typically, as I said, the centroid numbers are down to about 1/10 of a pixel. And so it's unlikely that that's causing you a problem. However, it may be an indication that the guide star is not well focused. If it doesn't have a reasonable peak to it, it might also happen when you're dealing with very long focal lengths or you have particularly bad seeing conditions. But the answer there is to really start by looking at your main images, deciding whether they're of adequate quality, and then looking at the numbers in the guiding performance for when those pictures were taken, and not worrying very much about what you see on the real-time display. For what it's worth, I never look at that thing at all unless I'm trying to figure out what my typical star sizes are.
Okay, using the ASCOM driver means PHD2 is sending non-cable, non-Ethernet cable messages to the mount. Does that mean anything to you?
Was that a question or an assertion?
I mean, I don't know, because it's got a question mark after it. And oddly enough, I think Bob might be the better person to ask that question to.
Well, okay, here's how this works. For most mounts, the ASCOM connection is done over a USB to serial connection. Some mounts, like the Los Mondis, have network connections, Ethernet connections. But it all depends on how the ASCOM driver was implemented. So if the ASCOM driver is sending commands over what it thinks is a serial link, then that's going to be over the USB connection. It doesn't make any difference at all. Those connections are all much higher speed than they need to be for the purpose of guiding. The amount of traffic that guiding generates itself is very low.
There was a mention of using PHD with Maxim DL. Where can I find information on that? Actually, that is a good question because I get asked this constantly.
Okay, if you go to the PHD2 website, I think there's a tab up at the top that's called News, and on that page, there's discussion of the dithering, the PHD2 dithering package, and that allows you to control dithering from MaximDL. And if you can't find it, just post a question on the PHD2 forum, the Google forum, and we'll send you a link to it.
Okay, I just sent them the link to the actual news part of it, so they should be able to find it. I have seen it before. Again, I direct people there as well.
All right, thanks.
Let's see if I can squeeze one more question in before somebody else interrupts us. Name's Richard Wright. Let's have a look. How do I use the periodic PEC algorithm? Oh, that was one thing that we can quickly run over. Should we open up PHD2 and show them the guiding assistant? Because I think that's something that we really wanted to go into.
Okay, just real quick, let's see if I can fire this guy up.
Right, I think you might have to exit out of the screen share and then share that particular program, otherwise we won't see it.
Yep.
And we can run over time by about 10 minutes. It's all good.
Okay, so you can see that?
Yep, perfectly.
All right. So what you do is you get connected to your gear. And then once you're guiding, you go into the guiding assistant, which is up here. Well, I guess I can just show you how this works. So you start looping, and you let PHD2 choose a guide star, and you start guiding. And once you're going, you go up here and you fire up the guiding assistant. And it's already going to be taking measurements. So, you know, this is how it works. You'll see there's a checkbox down here to measure the declination backlash. You might want to uncheck that if you've already done it many times. As I said earlier, there's no point in doing it over and over again. And then this is how you would run the guiding assistant. And it wants to run for at least 2 minutes to be able to get good, accurate data. So I'm not going to sit here and let it run for 2 minutes. But when you do, you can always go back and look at previous runs. And so here's one that was done sometime earlier, and you'll get these recommendations here. And these, you can go back and look at up to 3 previous GA runs if you want to, and you can apply whatever recommendations it makes. So does that answer the question, Simon?
Oh yeah, totally. I think people don't know where to find this or don't know how to utilize this particular part of PHD2.
Yeah.
And they tend to have all the numbers show up and they sit there and they fiddle to death with it, and they end up making it worse sometimes. Last question, which I can answer quite easily. William says, at 2800 millimeter focal length, is it better to use an off-axis guider or a dedicated guide scope? Generally speaking, I would say OAG or off-axis guider without a shadow of a doubt, because you don't want to introduce flexure into the system unless you know you can absolutely clamp down a guide scope so it doesn't drift off and wander around and do weird things. So yeah, I would always suggest doing off-axis guiders. There's plenty of them out there in the market. If you really want to go crazy with that type of focal length, I probably would use a on-axis guider from Innovation Foresight, because it's a larger area that it looks at.
Yeah, at 2800 millimeters, you're simply not going to be able to use, excuse me, a guide scope. It won't work.
Unless you have a 2800 millimeter guide scope.
That just will make it even worse.
Probably. All right. Can you address where the predictive PEC algorithm is? Oh, that's a good question. That is actually a good question. Where is that hiding?
Okay. So when you're not guiding, you open up the advanced dialog and you go to algorithms and you choose predictive PEC right here.
Oh, can you move the window to the right a bit? It's a little bit cut off.
like that.
Is it moving? Yeah, there we go. There we go. There we
Is
go.
that all right?
Yep.
Okay, and then there's a thing down here that's called period length. I don't know if you can see that or not. You should set that to be initially to be the whatever the worm period is on your mount. And that gives the algorithm a good starting point for starting to look at how the mount is behaving.
But a lot of the time you can set it just to auto adjust. So I mean, it just takes more time. That's all.
Yes, that's how I run with it. Yeah.
Yeah. So again, as a reiteration for everybody out there, the point of this presentation is to explain to you that PHD literally means that push here dummy. You don't need to obsess over all of these numbers. That's why the guiding assistant is there. That's why that brain icon is there to calculate all the algorithms for you, so you don't have to sit there and scratch your head over plugging in these numbers and things like that. So again, take full advantage of all the guiding assistant part of it and that brain icon to work this out. You've just got to plug in your focal length, and you just got to plug in the camera sensor pixel size, and you're pretty much all set.
Yeah, well, that's a good thing. Since we're trying to show people where these things are, a lot of people can't find the new profile wizard. So it's over here in the gear, in the connect equipment dialog, where you click on this USB icon. You click up here, and you have new using wizard, and that launches the new profile wizard. And this is where you choose your camera, you say what the pixel sizes are, what the focal length is for the guide scope, what binning level you're going to use. And this marches you through this. Then you choose the mount, you choose whatever other equipment you might have, an adaptive optics device or a rotator, which most people don't have. And then when you're all done, you have a profile that's already tuned up and ready to go. So this is the way that you want to do it if you're making any kind of changes to your equipment.
All right, so before we wind up, Jose, answer to your question is, every time you change your hardware and your mount, you need to rerun the guiding assistant. If you're using the same setup, you do not need to continuously run it. Okay, Bruce, we could probably go on for years upon end if we kept the stream running forever. I think we'd both die of old age by then. So thank you very much for doing this. I know 1 hour is a very, very relative short period of time. Just to give a quick plug to you, what you do and how they can get in touch with you guys, just give them a quick rundown of the website and how they can get in touch and where they can find the forum.
Okay, hang on just a second. I think I've got if I go back to the presentation,
Yep.
I think I can talk about that. So way down here at the bottom, okay, here's the support forum, and it's a Google group. It's open PHD2 guiding. I guess we didn't have a link here after all. Sorry about that. And that's the place where we can give you some help. We're always going to ask you for guide logs. I mean, we go through this all the time. People send us screen snapshots, or they try to describe what their setup is and then describe what the problem is. And that's all fine, but we can't really do anything without looking at the hard data. And that's tied up in the guide log at least, and sometimes the debug log. And we've made that easy because we have a built-in function in PHD2 now that will automatically upload those log files for you. So that's the best way to get support. There is a huge amount of help content with PHD2. Nobody ever looks at it, but you should, because it goes on for pages and pages. It talks about things in great detail, and it will give you more information than we probably can unless we want to sit there and type for several hours. So I encourage people to look at that before they have to go elsewhere and ask questions.
Excellent. All right, Bruce. Again, I really do appreciate it. Hopefully we can have you back on here again to do some of more of the advanced stuff, because this was initial deep dive into the whole thing, but PHD2 has a bigger section, shall we call it, for some of the advanced users, which is kind of beyond the push here dummy part of it,
Right.
I guess.
Yeah.
So
happy to do that.
excellent. Okay. We're going to take a short break. As you can see, Richard Wright is already raring to go. He was raring to go an hour ago. So we're just going to take a quick short break, and we will be right back. So don't run anywhere. Go to the bathroom. Go grab yourself a drink or whatever it is that you guys are doing, and we will see you again in hopefully 15 minutes.